So it's a pleasure to welcome or to introduce our third speaker for this session, Ritabrata Munshi from ISI in Calcutta and TIFR in Mumbai. He's noted for his recent remarkable work on subconvexity for L functions, particularly automorphic L functions on GL3. And he's going to talk to us about the subconvexity problem for L functions.
Thank you very much. So it's really a great honor to speak in the Congress. So I'm going to talk about this problem, which is basically about estimating some size of some holomorphic functions. Okay. So let me start by introducing the objects that I'll be looking at. So the first example is a Riemann function. As we all know, it's defined by the Dirichlet series and also given by an Euler product. So S is, I'm going to write S as sigma plus IT, where sigma will be the real part and T is the imaginary part. If sigma is greater than 1, then both the series and the product converges absolutely, and it defines an holomorphic function. And Riemann realized that to understand, study the number of primes of a given magnitude, you can, it's enough to study the analytic properties of the Riemann function. And to that end, he proved the two fundamental properties. One is the analytic continuation of the Riemann function, except the point s equals to 1. And he also proved the functional equation, which relates the value at s to the value at 1 minus s. Okay? So for the functional equation, you would multiply by a suitable gamma factor, which I'll call gamma rs. Okay, so here is another example of L function which behaves more or less similarly. Is the Dirichlet L function. Again, it's given by a Dirichlet series, and it's equal Euler product. And it has similar properties. It also satisfies the functional equation. Again, you have to multiply with a gamma factor. And now we have to multiply also by m to the power s by 2, where m is the modulus of the character. And here you'll see that actually the value of this L function, Ls chi, is related to the value of L1 minus s chi bar. Okay, so it doesn't really reflect back to itself unless chi is a quadratic character. So there's slight difference between the Dirichlet L function and the Riemann function. But the main similarity is that both of them are of degree 1. So if you look at the Euler factors over here, they are polynomials of degree 1 in p to the power minus s. Okay, so now I'm going to give an example of an L function where it's of degree 2. So you start with the discriminant form, delta z, which is given by this product, and q is e to the power 2 pi I z, where z is taken in the upper half plane. And one can actually expand this product into a series, and tau n's are defined as these coefficients in that series. And one can prove that there is this transformation property that delta of az plus b by cz plus d is related to delta z for all matrices a, b, c, d in SL2Z. Okay? So this is an example of what is called a modular form, or a cusp form of weight 12 and level 1. And Ramanujan conjectured that these coefficients are multiplicative, and for powers of prime, it's related by a recursive formula. And he also made this conjecture that the tau p's are bounded by p to the power 11 by 2, essentially. So if you normalize, since the size of these tau n's are like n to the power 11 by 2, we normalize it by dividing by n to the power 11 by 2, and then we can attach an L function to it. So Ls delta is defined by this Euler, this Dirichlet series, and this is equal to this Euler product. This comes from the first two conjectures of Ramanujan, which was proved by Mordell and later by Hecke. And again, one can show that it has absolute convergence in this half plane, and it extends to an entire function. And again, we have a functional equation which is almost same as what we had for Riemann function, relating the value at s to relate it to the value at 1 minus s. Again, we have to multiply with a suitable gamma factor. Here we have 2 copies of gamma r s. The main thing is the local Euler factors here are degree 2 polynomials in p to the power minus s. So these are examples of higher degree L functions. And so next, I'm going to introduce some other L functions which appears in analytic number theory. So suppose we have two GL2 or 2 modular forms, and where I'm writing the Euler factors as a product of 2 linear factors over here. So F1 and F2 are 2 modular forms, say. If I take chi modulo m, then I can twist the L function and define an L function of L as F1 twisted by chi, where the local factors are now given by this. So instead of alpha 1p here, I have alpha 1p chi p. Or you can take the Rankin-Selberg convolution, and here you see that this is still a degree 2 over here for the twist. For Rankin-Selberg, we have a degree 4. So the local factors here for L as F1 cross F2 has 4 linear Euler factors. So it's a degree 4 L function, and the symmetric square is defined in this way. Okay, so it was proved by Shimura that the corresponding this L function has a functional equation which is like the Riemann function. And it was proved by Rankin and Selberg that this has a similar kind of functional equation, right? So, so we have now seen L functions of degree 1, 2, 3, and 4. Okay, and you may ask what will be the general definition. So for phi an automorphic form for GLD AQ, we can define an L function, L as pi, which is a product of local L factors. And if we expand, we can get a Dirichlet series for that lambda pi n by n to the power s. And the local L factors are now Euler products of degree d, alpha 1 p p to the power minus s. So there are d many factors over here. And at infinity, we have to multiply with d many gamma factors and to get a completed L function, which will have a functional equation of this type, where you have to multiply by an integer q pi to the power s by 2 to get this functional equation. Again, the value of Ls pi is now related to a value of L1 minus s pi tilde, where pi tilde is the contragradient automorphic form. Okay. And it was shown by Gelbart-Jacquet that actually the degree 3 L function, the symmetric square, is associated with the automorphic form of degree for GL3. And it was shown by Ramakrishnan that for Rankin-Selberg L function, it comes from an automorphic form for GL4. Okay, so what is the main conjecture? It's of course the Riemann hypothesis, which says all non-trivial zeros of Ls phi are on the central line, half plus IT. And a consequence of that is the generalized Lindelof hypothesis. To state that, so it's about the size of this L function. So I have to define with respect to what will be the scale to measure the size. So here is the scale. It's called the analytic conductor. It's defined by this q pi. So q pi is the number which was appearing in the functional equation over here. So it's q pi times this product of d many terms, where this mu i's are the numbers which were appearing in the strips of the gamma factors. So that was like 2 slides back over here. These are the mu i's. And t is the point where you were computing the L function. So there are 3 different components which go into this conductor. So one is the level, q pi. And if you forget all the other parameters, the number of t's that appear is t to the power d. That's the t part. And the spectral part is if you take t to be fixed and q pi fixed, then you're basically taking a multiple product of the mu I factors. So that's the spectral parameter. Okay, so GRH implies that the size of this L function is bounded by the conductor to the power epsilon. So the size cannot really grow cannot become too big. So for any epsilon positive, you have this. So there is a C epsilon such that this is bounded by C epsilon times this to the power epsilon. And that is in analytic number theory, write it as this. So you forget the C epsilon thing. So it's bounded by C epsilon t, C pi t to the power epsilon, right? So it's just a notation. Okay, so what can you say? So using the functional equation and the fragment law of principle, we can say that L half IT pi is bounded by the conductor to the power 1/4 plus epsilon. Okay, so that's the trivial bound. It's nothing more than the functional equation over here. And that's called the convexity bound. Okay? And the subconvexity problem is trying to get a bound which will bit this bound by an exponent smaller than 1/4. So this is what we are trying to do. And now as in the conductor, there are three different things that are going into it, the level, the T, and the depth. So we can you can break the problem into three different things. One is the level aspect, and the T aspect, and the spectral aspect. Right? Okay, so why are we interested in such a problem? So the first application is the Hilbert's 11th problem, which asks, so if you take a number field and if you are given a quadratic form over a number field, then the problem is find which integers can be represented by that quadratic form over the number field. And so basically it's answered by Ziegel's mass formula, but in the case of Q, a positive definite ternary quadratic form, so it has three variables, then it doesn't really follow from Ziegel's mass formula in this case. You can then answer Hilbert's 11th problem if you have a subconvex bound for this twisted L function, L half pi twisted by chi. So where pi is now a fixed form for GL2AF, where F is the number field on which the quadratic form is defined, and chi is a Grossen character for this field. Okay? And this was, such subconvex bound was first obtained by Cogdell, Piatowski, Shapiro, and Sarnak for F totally real, and that gave Hilbert's 11th problem for F totally real. Okay, so the other related problem is Linux problems. It's about the equidistribution of points on a sphere. So you take a n, which can be represented as a sum of three squares. Then there are roughly like root n many points on that sphere. Then you project it down to the unit sphere, and you want to see how those points are getting distributed. And the conjecture of Linux was that they get equidistributed. And that, again, you can prove using the subconvexity bound for L half pi twisted by chi, where pi, in this case, will be just a modular form. Okay. Another related thing is the equidistribution of Wigner points on Shimura curves. And for this, you need a subconvex bound for some degree 4 L functions, the Rankin-Selberg L function, which was done by Philippe Michel and his collaborators between 2002 and 2006. So there are various applications of the subconvexity bound, and it's not really just about beating an exponent by something. So there's some meaning to it. So I was more or less motivated by this particular problem. It's called quantum inequality. So if you take x naught q, this is a modular curve of a level q, and there's a projection map from x naught q to x naught 1. Right? Let's call it pq. And suppose if you take a weight 2 cast form of level q, then you can define a measure, a probability measure on x naught q. And then using this projection, you can define a probability measure on x naught 1. Okay? So now as you vary q and you take f's in different q's and q is tending to infinity, you get different measures on x naught 1. And the problem is to find out how these measures are getting distributed on x naught 1. And the conjecture says that it will weakly converge to the uniform distribution. Okay. So, and it's known that it will follow from the subconvexity bounds for symmetric square L function and the symmetric square of f tensor G, where G is another GL2 form. Okay, so this is a degree 3 L function, and this is a degree 6 L function. So if you have subconvex bound in level aspect in both of them, then you have this weak convergence. Okay, so what do we know about subconvex bound? So how does one estimate the size of L function on the central line? One way is to use the functional equation again. And so from functional equation, we get something what's called the approximate functional equation, and that gives an expression of, say, zeta half plus it. It's bounded by supremum of Sn by root n, where Sn's are like partial sums, n to the power it. So this is the harmonics that appear in zeta half plus it. And this small n is running between capital N and 2n, and n has to be taken up to t to the power half. Okay? So if you just take the trivial bound for this, then you recover the convexity bound. Okay? And to get a subconvex bound, what you have to do is get some cancellation in this exponential sum. Okay, so there are various ways to estimate exponential sum due to Harman-Weil, van der Korput, exponent pair method, Vinogradov, and Pombederi-Vanich. It's like a combination of all these three. And so for example, from using Weil differencing, you can prove that the zeta half plus it is bounded by t to the power 1/6 plus epsilon. So this is the first example of a subconvex bound going back to 1920s, and it's quite strong because the convexity bound in this case is t to the power 1/4, and it's a drop from 1/4 to 1/6. Okay, that's like 1/12, right? And in the last 98 years, we have reduced it by 1/84. And it appeared last year. It's a paper by Gourvin. So beating the Weil bound is really difficult problem. And beating the Weil bound by a big margin is even more difficult, I think. Okay, so that's about the Riemann zeta function. So if you look at the Dirichlet L function, then the same procedure will land you to sums like chi n. So these are short character sums. So the n will be going up to square root of the modulus of the character. So these are short sums. So this lies beyond the region of Polya-Vinogradov. The Polya-Vinogradov bound will be just trivial in this case. And so the first person to get a non-trivial bound for such sum was Burgess. And he used an ingenious method to transfer this sum to a complete sum, which is a slightly complicated sum, but character sum, but it's complete. It's running over all x modulo m. And for this, you have the well bound, which is the Riemann hypothesis for curves. So you have square root cancellation over here. And the square root cancellation gives so much saving that it recovers the loss that you make while moving from the short character sum to a complete character sum, and gives you an extra saving over that. And that gives you this subconvex bound, that L half chi is bounded by m to the power 3/16 plus epsilon. The convexity bound is m to the power 1/4, 4/16. And this still remains a record. Okay. So the problem with the Weil method and the Burgess method is that it cannot be readily generalized to higher rank L functions. And so we need a general method. So the moment method is something more general, as you will see. So what we do in the moment method is we have such an inequality where the particular value of the zeta is bounded by the integral. And this integral is the difference of these two integrals, 0 to t plus g and 0 to t minus g. And if we define the moment m to t to be the integral of 0 to t zeta plus I whole square, and then it's the difference of m to t plus g minus m to t minus g. And if you have an asymptotic for this moment, then you can use that asymptotic to get a bound for zeta plus it. Right? And one can prove such an asymptotic. The leading term is t times a polynomial of degree 1 in log t plus an error term et, where the error term is basically some exponential sum. And so when you look at the difference of the main term, the leading term will just cancel and it will reduce to g. Okay, so basically the bound for the Riemann zeta function will depend on what bound you have for this error term, the exponential sum. And if you take the exponent pair KL, then you have this bound for the exponential, the error term here. For example, if you take the trivial exponent pair half of, then you'll get t to the power 1/3 plus epsilon, and this will recover the while bound. So the moment method also gives you the while bound. Okay, and this can be generalized, as I said. If you look at the degree 2L function, then again you can compute the moment. So f is, say, a modular form over here of level 1. And Anton Good showed that it's asymptotically t times a polynomial, linear polynomial log t plus an error term et. And he gave the bound that et is bounded by t to the power 2/3 plus epsilon. And using the same procedure, now it follows that the L value is then bounded by t to the power 1/3 plus epsilon. Okay. So this is the analog of the while bound, because this is 2. So the trivial bound is 1/2, and you're getting 2/3 of 1/2. So that's the while exponent. Okay. So in this case, the error term is not as easy as is in the case of Riemann zeta function. It's not exponential sum, but it's a shifted convolution sum involving the Fourier coefficient of the form f. Okay. And this he treated using the spectral theory of Laplacian. Okay. Utila gave a different approach where his treatment was just based on Voronoi summation formula, so it's less technical than the spectral theory of Laplacian, and ultimately it also gives the while exponent. Okay, okay, so here is what we are doing in the moment method, right? So if you want to prove a subconvex bound for L half pi naught, so if pi naught is a fixed automorphic form, then you hunt for a family F which contains pi naught, and you estimate the moment. Okay, L half pi square, summed over pi is in F, and then using the non-negativity of this, you get the bound that this is bounded by square root of the moment. And now, since the best you can achieve is the moment will be at least the size of the family, so you need, the family cannot be larger than q pi naught to the power half, because you want to beat q pi naught to the power 1/4, that's a convexity. So if you want here less than q pi naught to the power 1/4, you have to take f to be smaller than q pi naught to the power 1/4 minus delta, right? So the family cannot be too big. On the other hand, you need the family to be big enough so that you have some sort of orthogonality, because when you open up this absolute square, you will get this type of sums, and you want to do it and show that when m equals to n, you have the main term, and when m is not equal to n, you will get something small and explicit, so that we can continue. Okay? So that's the problem. So you, in one hand, you want the family to be not that big, and on the other hand, you want it to be big enough. Okay? And sometimes, and in case of GL2, it very often happens that the family that you end up choosing has exactly the size square root of the conductor of the L function that you start with. And in this case, you have to use the amplified moment method. So you have to now throw in a weight, which is called the amplifier, which will, where for the particular case pi equals to pi naught, the amplifier is larger than the average size. Okay? And if you can get hold of such an amplifier, then you can get a subconvex bound, even when the size of the family is like square root of the size of the conductor. Okay, in the case of, in the t aspect or in the depth aspect, this is quite easy because you can just shorten the integral or the sum over the spectrum. Then that is more or less like amplifying a particular point that you're looking at. But when you're looking at level aspect, it's a little tricky and you need some sort of arithmetic to construct the amplifier. Okay, so that's the amplification technique of Friedlander-Ivanet. So here's an example. So So it's f is a cusp form of level 1, and chi naught is a character, primitive character modulo m. And then you look at f twisted by chi naught, and you want to, the convexity bound, so f is fixed, chi naught is varying, so m is going to infinity. So this is the convexity bound, and you want to prove a subconvex bound. And the natural family to look at is the family of all twists. So you take all chi's modulo m and look at this. And here, the number of points in the family is like m, which is same as the square root of the size of the conductor, because the conductor is m square. And here, you look at the amplifier moment, and you pick this special amplifier, and that gives you a subconvex bound. Okay, so this was done by Dukefield and Ivanich. And so the first paper which gives the amplification technique was of Friedlander Ivanich from 1992. So they gave a subconvex bound for the Dirichlet function, which is worse than Burgess, but nevertheless subconvex. And then there's been a series of papers by Ivanich, Dukefield and Ivanich, a series of 7-8 papers in, between 1994 and 2001, which gives you the level aspect subconvexity for a degree 2L function, and then the paper of Sarnak, Liu E, which gives the weight aspect for the Rankin-Selberg convolution when one of the form is fixed, and then Michel Kolsky, Michel van der Kam, and Harkos Michel for the level aspect of. So using the amplification technique, this technique was very useful to deal with degree 1 and degree 2L function. Now it got stuck. I don't know. It's not working. Maybe I'll just. Oh, no, it's working now. Okay, so in 2010, Michel and Venkatesh proved a very general subconvex city result, and they gave a subconvex bound for the GL2L function L half pi 1 and the Rankin-Selberg pi 1 cross pi 2, where now their result is over any number field. Okay? It's not just over the field of rational numbers. And so it's a very general result, it's a beautiful result, and you can actually compute delta explicitly from their argument. And also the amplification technique plays a role in their work. Okay? So I'm not going to speak much about this, but this more or less solved the subconvexity problem for degree 2 and for Rankin-Selberg L functions completely. Okay? Okay, so now what can you say about degree 3 L functions? So there's a paper of Conrad and Ivanich where they proved the while bound for a Dirichlet L function. So m to the power 1/6 plus epsilon, where chi is a quadratic character. Okay, and their method is based on computing a cubic moment. And this works because you have this crucial thing that you have non-negativity of the values that you're adding. So there is some meaning in computing the cubic moment if the things are non-negative, because from there you can say something about the individual size of the L function. So that's their technique. And using that, they could prove the while bound in the level aspect for Dirichlet L function. And Xiaoqing Li first used this method to prove the T aspect subconvexity for symmetric square L functions. So again, the non-negativity of certain L values play a crucial role in her argument. So it's basically, this is like L half Fj twisted by sim square. Okay. And Valentin Blomor in the very next year used the same argument to prove the subconvexity for sim square F twisted by chi, where chi is a quadratic character. Okay, so these are the first, more or less the first two results in the case of GL3 function. And a few years later, I gave different proofs of the same result. So now pi is not just a symmetric square, it's any SL3Z Hecke-Maskas form. And I get the same bound as Cauchy-Lee t to the power 11 by 16th. And now if pi is SL3Z and so it's no more symmetric square, but still I have a subconvex bound where delta was small in my case, but it has been improved, and now I think you can get like 1 by 36 over here. Okay, so what was the idea? So it's a slightly different approach. So you have from the functional equation, again you go to these partial sums, lambda pi n, so the Fourier or Dirichlet coefficients of the automorphic form pi n to the power it. So you are trying to get some cancellation in such a sum where the length of the sum is square root of the conductor, so it's going up to t to the power 3 by 2. So the idea is, so there are two types of oscillation that are playing a role here. One is the oscillation of the Fourier coefficient, the other oscillation of n to the power it. So you separate the oscillation. So the problem is to show that the correlation is small. So you separate them. So you can do it using, so delta nm is 1 if n equals to m and 0 otherwise. And you can detect this event using circle method. So this is one formula, one form of circle method. This is due to Klosterman. And so there are two parts in this formula. This is the analytic oscillatory part, and this is the arithmetic oscillatory part. Okay, and the magnitude of analytic oscillation here is given by n by c square. Okay, because n and m are of size capital N, and AC is roughly of size c square. So, so the idea is just you just plug in this over here, and that separates lambda pi n from m to the power it. Okay, and this is what you get. Okay, so usually you'll pick c to be, so c is the modulus in the circle method. You pick it to be square root of the length of the equation, which is n, and that minimizes the conductor c times d in the circle method, and it gives an expression of this form. And this you can think of as, so initially your problem was to compute this sum. This is like a correlation. This is the inner product between the vector lambda pi n and n to the power it, which is this. And here what you have is more or less the inner product of the vector lambda pi n with this trigonometric polynomial, trigonometric function, and m to the power it with this trigonometric function. So it's like an expansion with respect to some basis, where the basis comes from the circle method. Okay, and then the idea is just use some Poisson summation here, Voronoi summation formula here, and once that gives you some saving, and then you use Cauchy to break the involutory thing, and then again you apply another Poisson summation formula, and this works. Okay, but there is one crucial point over here, is that you need to, so when you plug in the circle method, you need to synchronize the new harmonics that you are introducing the circle method with the existing harmonics, so that the conductor becomes smaller. Okay, so this you do by not picking c to be square root of n, but by picking n to be slightly smaller than square root of n. So because you already have this analytic oscillation m to the power it present in the problem. So that's already inbuilt in the problem. So now by doing that, what's happening is that if you pick c smaller than that, you'll be left with some residual oscillation in the analytic part. But that's okay, because you already have an analytic oscillation in the problem. Okay? So that's what you do. And then you get something like a triple Klosterman refinement. So you get a cancellation in the A sum, you get a cancellation in the C sum on average, and you also get a cancellation over the integral x. Okay? And that works finally. Okay, so, but this doesn't work for the twist by character. So for that you need to do something slightly different. So you need a different version of the circle method. So this is another version of the circle method. It starts from the Peterson formula. So we are summing here over Fourier coefficients over a Hecke basis of level q, Niventable psi, weight k, and this is delta nm plus this off-diagonal term, which involves the Klosterman sum and the Bessel function. And then we take average over psi modulo q, q in running over some set, okay, and k is of size capital K, say. Then we get a formula where delta Nm now looks like there will be a one term which will involve the degree 1 harmonics. So this will only involve the trigonometric functions like the usual delta method of Klosterman or Diuk-Friedlander-Ivanich. But there will be another term which will involve the GL2 Fourier coefficients coming from here. So this is a different form of circle method. I call it GL2 delta method. Okay, and the GL1 part here looks slightly different. So after some reduction, it looks like this. So this is the analytic oscillatory part, and this is the arithmetic oscillatory part. The good thing is A is not involved in the analytic oscillatory part. It's over here. C goes up to n by q k square. Now you have an extra sum over q also. Okay? And this is like the x integral that you have over there. So this is a different version of the Klosterman circle method where you have an arithmetic sum instead of the analytic integral. Okay, and this q sum plays an important role because you get cancellation in A, the cancellation in C, and also cancellation in Q. And that gives you the subconvexity for the twist of GL3L function. Okay. Again, there's a conductor lowering mechanism is required over here. That you do by choosing the forms in the Peterson formula to be of level Q times M, where M is the modulus of the character chi. Okay. All right, I'll not go into further details here. But you can use the GL2 delta method to prove other things. For example, you can prove the level aspects of convexity for symmetric square L function. And recall that for QE, you need level aspects of convexity for symmetric square and symmetric square across G, where G is another GL2 form, fixed form. And Paul Nelson showed that that follows from this one, okay, with some work. And so jointly, we have proved the arithmetic quantum inequality. So that's one thing that you can get from GL2 delta method. And now, in the last 2-3 years, I've been looking at what you will get if you use the GL2 delta method in the more classical problem of bounding degree 1 and degree 2L function. So it happens that if you use the same method, then you recover the Burgess bound for both GL1 and GL2 in a uniform manner. And if you do the same thing for in the T aspect case, you get something better than the goods bound. So this is something, it's sub-while. Okay. So the thing is, the drop in conductor is bad news for amplification technique because that will mean that you have to look at a higher moment. But it's good news for circle method because lower the conductor, more powerful is the circle method. So that's one point that helps here. And so I also mentioned that there is a recent work of Olowensky and Paul Nelson where they simplify this GLD delta method in such a way that in some instances you really don't need to really go back to the Peterson formula. So it's kind of a short circuit which burns the first few steps. Okay, so what lies ahead? So basically, this is a method to compute correlation of two sequences, A and Bn, and where we need at least one of them to have an automorphic origin. So here are some example where we have such a problem. So if you're looking at the second moment of the Riemann zeta function or the Dirichlet divisor problem, then you end up with sums like this, where dn e square root of nx to the power 3, where n is going up to x. So this is kind of it's a bad GL1 oscillation, where it's not automorphic, but this is automorphic. So you can try to use that, and probably you'll get something beyond what is known in these two cases. And also, if you are looking at sums of Fourier coefficients, so suppose f is a GL2 form, and you look at the sum of the Fourier coefficient of a sharp cut here, so this is the analog of the Dirichlet divisor problem, then there is a long-standing barrier here that this is bounded by x to the power 1/3 plus epsilon. So that comes from Voronoi. And to improve this, what you need is you need some cancellation in this type of sum, lambda fn ea square root of nx cubed. So it's almost same as what you have over here, but this is even better because you have Fourier coefficient instead of dn. So maybe you can use the oscillation of this. Okay, and here also you can try to use the same method of GLT delta method to separate the oscillation and see what you can get. And hopefully one can go past x to the power 1/3 also here. And finally, I would like to mention this problem about, it's known that for degree 1 and degree 2L function, there are infinitely many zeros on the central line. But for the symmetric square L function, it's not even known that a single zero lies on the central line. So for that, so if you want to prove Hardy's theorem, which is saying that there are infinitely many zeros on the central line, you have to prove such a bound like this. So lambda pi n, the Dirichlet coefficient of symmetric square L function, this twisted by a n to the power 2/3 must be bounded by x to the power 5/6. So it's not just a non-trivial bound, you need a substantial saving in the bound. And if you get that, you get infinitely many zeros of a symmetric square L function on the central line. And this is again something that may follow from the GL2 delta method. So here's a list of problems that one can try, and hopefully one can do much better than what is known already. So I'll stop with that. Thank you.
Are there any questions for Ritabrata?
There's some connection between bounding an L function and computing it algorithmically. So the convexity bound is related to the fact you can compute it in time that's the square root of the conductor. Do any of the techniques you're talking about allow one to compute faster than square root of the conductor?
Yeah, I really haven't thought of that, but yeah. So Roman actually mentions that it probably can be done that way, so, but I haven't spent time on that. Yeah. Yes.
Since you mentioned the Hardy problem at the end, do these bounds pertain to showing that some large proportion of the zeros at least lie on the critical line?
You mean for the Riemann zeta function or something?
For example, or some of the other L functions that you're talking about. I mean, can you, these are famous theorems in special cases.
I have to see. So if it boils down to something like finding correlation between sequences like A and B, and where one of them are automorphic or a divisive function, then probably, I mean, it really depends whether, you have to really work it out to see whether it works or not.
Okay.
So,
Are there any other questions or comments? If not, I'd like to thank the speaker again for his lecture.